Hello everyone, let's look at our next problem. Show that linear independence is preserved by one-to-one transformations, and that spanning sets are preserved by onto transformations. More precisely, if T mapping V to W is a linear transformation, show that if T is one-to-one and the set V1 to Vn is linearly independent in V, then TV1 up to TVn is linearly independent in W. And if T is onto and V is equal to the span of V1 to Vn, then W is equal to the span of TV1 to TVn. Okay, so I think this is just going to be playing around a lot with the definitions of one-to-one and onto, linear independence, span, and all that stuff. It's been a long time since I've seen the phrases one-to-one and onto, but those, of course, mean injective and surjective. So let me write out the first part of the problem here. Okay, so the first statement we want to prove, if we suppose that T is injective, we want to start with a linearly independent set, apply the transformation to each of these vectors, and we want to prove that the set of vectors we end up with is also linearly independent. So I'm going to start with a little bit of rough work here before, I don't see exactly what the path is here, but I think it's just going to be writing down definitions of things and kind of manipulating them. Okay, so this ended up being pretty straightforward. Again, just write down the definition and then something came to mind immediately. So we want to prove that if this set is linearly independent, then this set is also linearly independent. So I'm going to start with this equation, and I want to prove that all of the coefficients a1 up to an must be equal to 0. So I'm basically just like using properties of linear transformation to undo. Each of these going from one line to the next is just using a property of linear transformation. So I bring a inside like this, and I do that for every term. So this a I bring inside like this, and then I have t applied to a whole bunch of, or t of a whole bunch of terms added up, and I can, it looks like factoring out the t, but it's not exactly that, I suppose. So I now have that this is equal to 0, but t is injective. So if t of something is equal to 0, then that something has to be equal to 0. Now we use the property that the set of vectors v1 to vn is linearly independent. If this adds up to 0, then all of the coefficients must be equal to 0. And so we're done. We've shown that if this set is linearly independent, then so is this one. So let's move on to the second part of this problem. Okay. And I'm going to use a very similar idea to what I had previously. I don't even think I'll have to go through the rough work here. We're assuming that the vector space V is equal to the span of V1 up to Vn. We want to prove that the vector space W is equal to the span of TV1 up to TVn. So what I'm going to do is I'm going to say let W be a vector in the vector space W. Okay. This means W is equal to A1 T of V1. Sorry. This means that W is equal to T of V for some vector V in the vector space capital V. And that's because T is surjective. Right? T being surjective means we can always find a vector V such that W is equal to T of V. It may not be unique, but we don't care. Now, because V is an element of capital V, this means there exists A1 up to AN such that V is equal to A1V1 plus dot 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 a n v n. And this is because v1 up to vn spans v, as given. Okay. And now we just go back to here and we substitute this expression, this, in for v. So this says that w is equal to t a1 v1 up to an vn. Use properties of linear transformations. This is now a1 tv1 plus dot 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 plus an tvn. And because w is arbitrary, right, we let w be any vector in the space capital W, and we've now written it as a linear combination of tv1 up to tvn. So this says that w is equal to the span of tv1 up to tvn. Yeah, so again, essentially just writing down definitions of what these things mean, playing with them and kind of piecing them together. It helped that I had done part A before doing part B. I kind of saw immediately what to do in part B after having gone through the steps in part A. Yeah, but a nice little question testing whether you can sort of simultaneously use different definitions of these ideas for linear spaces and transformations. If I have any more to say about this one, I'll write it down in the description. Thanks for watching.